Hi students, welcome to physics class. Today we will discuss about Doppler effect. Doppler effect is defined as the phenomenon of apparent change in the frequency of sound heard by the observer due to the relative motion between observer and source. The Doppler effect is observed only when there is relative motion between source and observer. That is, let us consider there is source of sound and here is observer. Whenever source of sound and observer are at rest, there is no Doppler effect. We will not observe any Doppler effect when the source and observer are at rest. We will observe the Doppler effect only when source is moving towards the observer or source is moving away from the observer, or observer is moving towards the source or observer is moving away from the source, or the source and observer are moving towards each other, or the source and observer are moving away from each other. These all 6 cases are referred to a relative motion. The observer and source are moving with respect to each other, then only we observe there is a change in the frequency. This change in the frequency is called as apparent frequency. This phenomena of changing the frequency of sound due to the relative motion between source and observer we called as Doppler effect. Let us consider source of sound and observer. Let us suppose source of sound is at rest, that is velocity of source of sound is 0, and observer is also at rest, that is the velocity of the observer is also 0. If the source produces a sound wave, then it reaches the observer with one crest and one trough. That is, the distance travelled by the wave is equal to the wavelength. Suppose the source is moving with velocity Vs, then at a time period t, the distance travelled by the sound wave is given by t is equal to velocity of sound wave into time. The distance travelled by the wave is equal to velocity into time. In this period of time, the source is also moving with a velocity Vs. Therefore, the distance travelled by the source is given by Vs into t. Here, Doppler effect can be observed only when the velocity of source or the velocity of observer is less than the velocity of sound. If the velocity of the observer or the velocity of the source is equal to the velocity of sound, then Doppler effect is not observed. This is the limiting condition for Doppler effect. So, let us consider a case, it is the case 1, in which the source is moving towards the observer. The velocity of source is Vs, the velocity of observer is 0. That is, the observer is at rest and the source is moving towards the observer. The distance travelled by the wave to reach the observer is lambda, which is given by the product of velocity of wave and time period. That is, in a time period t, the wave covered a distance of lambda. During this time period t, the source is also moving and the distance travelled by the source is given by Vs into t, because distance is equal to velocity into time. Here time is called as time period of the wave. So, the remaining distance is given by lambda dash. From the figure, we can clearly say that the distance between source and observer initially is lambda. The distance travelled by the source is Vs into t, and the remaining distance called as apparent wavelength is given by lambda dash. By separating lambda dash, we get lambda minus Vs into t. We know that time period is equal to inverse of frequency. Therefore, lambda minus Vs into 1 by n, that is equal to, by taking LCM n, we get n lambda minus Vs. We know that V is equal to n lambda. Velocity is equal to frequency into wavelength. That is equal to V minus Vs divided by n. This is the apparent wavelength. This is called as apparent wavelength. Apparent wavelength. Next, we will calculate apparent frequency. Apparent frequency. Apparent frequency can be calculated as n dash is equal to V by lambda dash. Here, in this expression, we will separate n, then we get V by lambda. So, n dash is equal to V by lambda dash. Here, the change in the frequency, that is apparent change in the frequency, is due to the change in the wavelength only. Here, the velocity remains constant. That is equal to V divided by V minus Vs by n. By taking n to the denominator, we get V by V minus Vs into n. This is the expression for apparent frequency when source is moving towards the observer. From this expression, we can clearly say that the fraction V divided by V minus Vs is greater than 1, because the numerator is higher than the denominator. So, the fraction value we get is greater than 1. So we can say that the apparent frequency heard by the observer is always greater than the actual frequency. Similarly, when the source is moving away from the observer is at rest, so its velocity is 0. The source is moving with velocity Vs. Then we can derive the expression for the apparent frequency by assuming that lambda dash is equal to lambda plus Vs into t. That is the distance travelled by the wave to reach to observer is increased in this case by a factor Vs into t, because this factor is arised by the motion of the source of sound. So finally, by taking negative values to positive, we can derive the apparent frequency in the same procedure, that is equal to lambda dash is equal to n lambda plus Vs by n is equal to V plus Vs by n, which is equal to current wavelength. Apparent frequency is given by V by lambda dash, is equal to V divided by V plus Vs into n. N dash is apparent frequency heard by the observer. In this case, the factor V by V plus Vs is always less than 1 because the numerator is less than the denominator. So the fraction value will be less than 1. Therefore, we can clearly say that the apparent frequency heard by the observer will be less than the actual frequency. Thank you.